Hello, welcome to another session on Vidyanidhi channel on embedded system design. So in this session, we will discuss about communication interfaces used in the embedded system. So each communication interfaces, whether it's an onboard or a system interface, we will discuss one by one. First, we will see what is exactly communication interface is. When we have an embedded system, the embedded system may consist of various subsystems. Those subsystems need to communicate with each other for the smooth operation and proper function. For that, we need communication protocols. So, depending on which are the subsystems which are communicating, different protocols are designed for efficient utilization and error-free communication between the subsystems. So these communications can be broadly divided or classified into two categories based on the prospects. One is device or a board level communication. On a single board, different ICs try to communicate with each other and exchange the data and information required for the operation. So such communications which are on board will use I2C, SPI, CAN, UART, iWire, etc. These are some communication protocols which are used in device or board level communication type. Another type of communication is product level communication. In this type, data transfer can happen between the two subsystems either in a wired manner or wireless manner. If it is a wired, the protocols such as UART, USART, Ethernet, USB, these are some wired communication protocols. If it is wireless, then it may be a infrared or a Bluetooth or a Wi-Fi or GPRS, etc. So depending on whether it is a wired or a wireless, a respective protocol will be used for the communication. So now we will go through the protocols. Not exhaustively, but whatever the important protocols we'll discuss one by one. The first protocol what we discuss is I2C or inter-integrated chip communication. So as the name suggests, it is the communication between the ICs which are on the same board or a single motherboard. On a single motherboard, we have multiple ICs and they try to communicate with each other. In such type of requirement, the I2C protocol can be used when we want to communicate between the ICs on the same board. So this basically works on the principle of master-slave type of communication. So one device will be operating as a master and other devices will be operating as a slave. Here we can also have multiple masters. Master are the ICs or the modules which actually initiate the communication. Slaves are the one which respond to the masters. So this type of protocol support must multi master communication. In I2C, it is basically a synchronous communication. So when we say it is a synchronous communication, usually handshaking signals are not required. Directly it can start communicating with each other. So it is basically a synchronous, bidirectional and half duplex communication protocol. As I said, synchronous, we don't need a handshaking signals. Bidirectional, the communication can happen between both the direction, that is master to slave or slave to master. But it is a half duplex. At any given time, only one side communication can happen, either from master to slave or from slave to master at any given time period. That is called half duplex. Okay. Then we use two wired connections are used in this. That is, one is serial control line, another one is a serial data line. So two lines will be used to connect. SCL is basically a control line used to synchronize communication, and SDA is used to transfer the information bits. Both SCL and SDA lines are an open drain. Thus, they need to be pulled up using a resistor to a logic high value or a VDD value. Both will be pulled up. So we will be using a pull-up resistor in the circuit because they are a open drain. Significant features of I2C protocol is its clock stretching. What is clock stretching? We will discuss in next slide. So in this slide, we can see how exactly the communication is done. And first we see the block diagram where we can see two slaves connected to a single master. Here we can see that SD and SCL lines both are pulled up to VCC using a 2.2 kilo ohm resistor. So there are resistors connected to both SCL SDA, that is the serial clock and serial data, and it is pulled up to VCC as there are open drain connections. So that SCL SDA are together called as I2C bus. So in this block diagram, we can see EEPROM and other device as a slaves, which will be communicating with a microcontroller or a microprocessor. So in this type of communication, if you see the next block, where you can see a clock signal, SCE and SDA data variation of the digital signal, how the digital signal is varying depending on the information bit, whether it's 0 or 1. So here the data, whatever the data has to be sent, when it is clock is high, the data status should not change. The protocol should make sure that whenever clock is at logic high or logic 1, the status of the data signal should not change. The data will change from 0 to 1 or 1 to 0 only when clock is logic low. Again, when the next time clock becomes logic high, whatever data is available on the data pin, that will be sent over the bus. If at all the data line, SDA line, changes from logic high to logic low when clock line is at logic high, then it is considered as a start of communication condition. Similarly, if SDA line changes its state from logic low to logic high when clock signal is at logic high, then it is considered as a stop condition indicator. So start and stop conditions are indicated by change of state in the SDA line when serial clock is at logic high. Otherwise, whenever data is communicated, we can observe in second block that always the change of data happens when clock is at logic low. The status of the SDA will not change when clock is logic high in the data communication. Only when we want to indicate a start condition or a stop condition, in those cases only the SDA line changes its state from logic high to logic low or logic low to logic high when clock is at logic high. In the third block, we can see the protocol, how the bit format. So first bit will be a start condition bit, that is change of SDA line from logic high to logic low when and keeping the clock at logic high. Then next, once the communication is started, then data information bits are sent. So before sending the information, we should know to which slave we are sending the data, as there can be a multiple slaves connected. So first we have to send a address, that's called address frame. This address frame can be of 7 or 10 bits. So that address will identify which slave has to be communicated. Then read or write bit will be sent. If the bit is logic high, then it is a read operation from the slave. If the bit is at logic low, then it is write operation. Once we receive the acknowledgement, that is the slave is ready to receive the bits, then actual information bit starts sending in the frame of 8 bits in each frame, that is data frame. After every data frame of 8 bits, an acknowledgement is received from the slave to the master. This is how the communication happens in the I2C protocol. Next, we will see what is SPI, that is serial peripheral interface. Again, this is also synchronous, bidirectional, full duplex, 4-wired interface. I2C is a half duplex, whereas SPI is a full duplex. Both are synchronous and bidirectional, but this one is a full duplex. So both the slaves, master and slaves, will be able to communicate simultaneously in the full duplex communication. Here you will have only one master and we can have multiple slaves. However, the multi-master system ecosystem can be designed, but it is a little bit complicated. But while designing, we should make sure that only one master is active at a time. So because protocol does not take care of arbitration, as in case of I2C, here the developer or a designer himself has to take care that any one master is active at a time. If that is confirmed, then multi-master can be designed. Otherwise, SPI will be operating with a single master and multiple slaves. So this will have 4 different signals, that is master out, slave in, that is single line carrying a data from master to slave, that is also known as slave input or a slave data in. Then we have a master in, slave out, so signal line carrying a data from slave to master device. It is also known as slave output or slave data out. First one is the input, slave input, second one is slave output. Similarly, master out means master will be sending the data, slave will be receiving. In, master will be receiving the data, slave will be sending. Then for synchronization of the communication, we need a serial clock, that is S clock, that is a serial clock used to synchronize the communication. And then we have the slave select, as we already discussed that there can be a multiple slaves. So the slave has to be selected. If there is only one select line for the slave, then only 2 slaves can be connected. And if there are 2 slave select lines, then we can have up to 4 slaves interfaced. Similarly, the number of slaves which can be interfaced depends on 2 to the power n, where n is a number of select lines, that is slave select lines. Here we can see how exactly the communication happens. First, the bus master configures the clock using a frequency supported by the slave device. That is because usually the masters will be operating at a higher frequency than the slave devices. So always the frequency will be set to, or the configure to, slave device frequencies. Then master selects the slave device with a logic level 0 on the select line. Whichever slave has to be selected, accordingly the slave line will be set, and that particular slave IC or the slave device will be selected for the communication. Then during each SPI clock cycle, a full duplex data transmission occurs. Once the clock is configured and slave is selected, then the communication begins. Then the master sends the bit of a MOSI line, and then slave reads it, while the slave sends a bit and master received it or reads it. So both MOSI and MISO can happen simultaneously. That is, master will be sending out bits on the MOSI line and slave will be receiving them. At the same time, slave also can send a information and on the MISO line where master will be receiving the data. This sequence is maintained even when only one direction data is initiated or intended. Even then, the similar pattern has to be maintained, whether it is a one directional communication or bidirectional communication. Then we have here we can see that master and slave, how the shift registers are used to send the data and receive the data. And in the another block, we can see the actual connection, how it is done. We can see that there are four signals actually required. Here there are three select lines and one MOSI, one MISO, and one serial clock. As we already know, serial clock is for the synchronization. Master out, slave in. Whenever master sends the output, slave receives the output. So it has to be connected to the same pin on the slave end as well. When we are actually doing the hardware connection, we should make sure that MOSI is connected to MOSI and MISO is connected to MISO pin only, so that the communication happens smoothly. Then the select lines, whichever are there, depending on the activation of the select lines. So that is the active low signals. So whichever the select lines we want to select, that particular bit can be made 0, and that particular slave can be selected. Then we have next protocol, that is UART, Universal Asynchronous Receive Transmit. So first two protocols what we just discussed, that is I2C and SPI, both were synchronous protocols or synchronous communication, where handshaking signals were not required. Whereas in case of UART, this is a asynchronous communication. Therefore, the handshaking signals are required before actual data is transmitted or received. So here data format and transmission speeds both are configurable depending on the type of the device what we use. The baud rate has to be set for that. So, but the standard baud rate for the UART communication is 9600 baud rate, which is usually supported by most of the communication devices across the commercial bandwidth. So usually 9600 baud rate is set for most of the communications. It is a serial, so serial data transmission. So one bit at a time will be sent one by one. The bits will be sent one by one from least significant to most significant, framed by start and stop bits. So there will be a start bit and a stop bit, between which you will have a 8 bits of a data, that is from least significant to most significant bits will be sent one by one. So in this type of communication, there are two common signal levels which we use. One is RS-232, which uses a 12 volt system, and RS-485, which uses 5 volt system. So if we are using RS-485, which is a 5 volt system, then usually we don't face much problem in the hardware implementation, because the 5 volts implementation is compatible with the standard TTL logic, that is the IC which are designed are basically on the transistor logic, that is a type of IC design or a transistor design configuration. Whereas RS-232, we have 12 volt system where 0 and 1s are indicated by 0 volt and 12 volts. So in that case, we need to have an interfacing IC called MAX232. That MAX232 will convert this RS-232 voltages into a standard TTL voltages, and then it will be processed by the digital circuit in the ICs. So whenever we use RS-232, then we need to use MAX232 also, which will convert the 12 volt system to 5 volt system. Then the communication may be in 3 modes. So it can operate in simplex mode, full duplex, or half duplex. In simplex mode, we know that it is only one direction communication. Either only one device will be communicating and otherwise just receiving. So once the receiver is set, then that cannot communicate back. It is a one-way communication. So that is a simplex. Then we have, it is like similar to a broadcasting system. If you observe a FM radio or a broadcasting system, they are a simplex system. They only communicate one side. We cannot communicate back to the FM station or broadcasting stations. We only receive the signal. That type of communication is simplex communication. Full duplex communication, both the devices can send and receive at the same time. Best example is our mobile, where simultaneously both the receiver and caller and the called party and calling party both can talk simultaneously, and communication will happen on both the directions. Whereas in the half duplex device, bidirectional, it is also a bidirectional communication, but only one device will be communicating at a time. That's like a walkie-talkie, wherein a receiver or a transmitter has to set the signal and then send the information. So only one way it is communicated at a time. After that, they start receiving. That is a half duplex. If we see the operation of a UART, there is a start bit and then the data frame, 5 to 9 bits. Then we have a parity bits, 0 to 1. So parity bit will be used to check the error while communication. And then we have a stop bit. So there will be a transmit register which will store the configuration for the transmission. Then shift register is actually having the bits to be transmitted. Depending on the clock frequency, the shift register data will be transmitted over the TX line. Similarly, when we want to receive the data will be received in the RX line. RX is a receiver line. Again, receiving will be serially, it will be received into a shift register, and then receive register the data will be transferred to receive register. So this is a general flow of how exactly a communication happens in UART. These till now we have discussed all the communications which were wired. So now we will discuss wireless communication. The first one is IRDA, that's infrared communication or infrared data association. So infrared provides a specification for complete set of protocols for a wireless communication. The main reason why we use infrared is that it can operate very efficiently when it is the distance is less than 1 meter using point to shoot principles. That means exactly it will point out where to communicate and it will communicating in the line of sight communication. That is LOS, that is line of sight communication. So this is basically an optical communication. So the data will be very much secure here, but the transmitter and receiver should be in line of sight. There should not be any obstruction in between the transmitter and receiver. Only then infrared communication can work. So as it is an optical communication and line of sight, it is a very low bit error rate. BR is very less and makes it very efficient communication. So physical layer of IRDA will have optical link definitions. So and modulation, coding, cyclic redundancy check, and the framer. These are the things which will be taken care by the physical layer implementation of IRDA. That is optical link definition means it will have the frequency at which the data has to be transmitted. Then modulation technique is used to modulate the signal and transmit it over. Of course, after modulating, if it has to be coded using binary bits. Then cyclic redundancy check is used to check if there is any error in the transmission. However, the error is very less, probability of error is very less in this type of communication. Different data rates use different modulation and coding schemes. The data rate here can be set configurable. So depending on which data rate used, different modulation and coding techniques can be used in the IRDA. Then the next we discuss about the Bluetooth communication. This is another type of wireless communication again. Again, Bluetooth is also a short range wireless technology that is standard that uses UHF radio waves, ultra high frequency radio waves in ISM bands. That is in the range of 2.402 to 2.48 gigahertz. It is a non-licensed frequency band, and at both the lower and the higher end, it will have guard bands. So it's about 2 megahertz wide at the bottom end, that is at the lower end, and 3.5 megahertz guard band at the higher end. So they are called as the guard bands in the personal area network. The transmission power is limited to 2.5 millivolts, uh, giving it a very short range of in about 10 meters. The maximum distance of transmission cannot be more than that, because the transmission power is limited to 2.5 milliwatts. That's the maximum transmission signal power. Again, as we said, it is uses a radio technology. It is a RF frequency communication. So here we use a frequency hopping spread spectrum. Frequency hopping spread spectrum means what happens is, even while transmitting a particular bit, the frequency keeps changing in a same bit. The different frequencies are used to transmit the same bit. So what happens is, even if one frequency is interfered by the noise signal, another frequency will be able to communicate. So the communication efficiency will increase, and as the different frequencies are used to communicate the same data bit, it is called spread spectrum. There is a spectrum of frequencies used to communicate. Uh, so here packets are created, divides overall data is divided into a transmitted data into a packets, and transmit each packet on one of 79 designated Bluetooth channels. There is 79 designated Bluetooth channel. Each channel has a bandwidth of 1 megahertz. So these bandwidth of 1 megahertz, that is 79 channels, are used to hop the frequencies. So there will be 79 different frequency channels available. Each channel will have a bandwidth of 1 megahertz. So the data transmitted can be any of these 79 channels in a particular packet. So even if one particular frequency is interfered by the noise signal, the other frequency will be able to communicate. It usually performs 1600 hops per second. So we can observe that the hopping is very, very high. That is 1600 hops per second. Uh, Again, hopping, as we already said, the hopping is nothing but changing the frequency from one channel to another channel among the 79 designated channels. So this Bluetooth can communicate maximum up to 7 devices in a particular piconet. So we can see a Bluetooth module also there. Small picture is given for just indication that that's how the Bluetooth module looks like. Then we have Wi-Fi. This is another type of wireless communication. So this is basically this is it is an Wi-Fi itself is not actually a technical name. It is just a brand name used for the IEEE 8.2.11 communication protocol. Technically, it is IEEE 802.11, but generally it is known as Wi-Fi. The name is widely used as a Wi-Fi, which operates at a 2.4 gigahertz frequencies. That's 120 mm, ultra high frequency, and 5 gigahertz at a 60 mm wavelength. That is super high frequencies. These are the two radio points. Again, these are unlicensed. That's 2.4 gigahertz as well as the 5 gigahertz. 2.4 gigahertz is the ultra high frequency, 5 gigahertz is super high frequency. So these are will have relatively high absorption rate. So again, these are work very efficiently if we have a line of sight communication. Otherwise, there will be small error might happen, but still the communication can happen. Wi-Fi will still communicate even if there are obstructions. but it will work best if it is a line of sight. It doesn't mean that it will not work without a line of sight. It does work. Even Wi-Fi can work from in an entire home. It will work even if you keep a Wi-Fi module in one room, and if you are working from the other room also, it will work. But the speed of communication will be very high if we are in the line of sight with the transmission module. An access point, that is usually a hotspot, often has a range of up to 20 meters in the indoor area. In the outdoor area, again, it depends on the landscape and the buildings available on the surroundings. That all depends. So in the indoor, on an average, it will be 20 meters is a range of a Wi-Fi. Uh, some versions of Wi-Fi running on a suitable hardware at a close range can achieve speed up to 9.6 gigabits per second. Not all Wi-Fi will achieve this speed, but only few versions of the Wi-Fi can achieve this type of high frequencies or a high data rate. There is a MAC address which is used to specify both destination and source of the packet data. That is a media access control address. MAC is an address given to each device. Uh, that MAC address is used to identify the particular device. So again, the channels are used as a half duplex and can be time shared by a multiple network. So again, at any given time, a particular channel can be used only to communicate in one direction. That is half duplex. In the same channel, we cannot transmit the data simultaneously on both the directions. In only one direction, we can send the data. However, if we want to send the data in both the direction, or we want to send the data in the same direction using a multiple devices, then time sharing method is used. Then another protocol we have is a Zigbee protocol. This is quite latest. It is again a format of IEEE 802.15 protocol. It is zero point 0.4 based specification. It is also high level communication protocol, but it is a low power communication. But again, data rate is also low. Whenever we are operating with a lower data rate, say simple operations or simple applications of access control applications, where whatever data is transmitted or communicated is very small amount of data, then we can use a Zigbee. Especially in the access control IDs, we use a Zigbee protocol, because there the data what has to be communicated is a very small amount of data has to be communicated. So there we can use a Zigbee protocol there. When we have a large amount of data to be communicated, then Zigbee is not a suitable protocol there. So depending on the application, a particular protocol has to be chosen. Again, this is a close proximity wireless ad hoc network basis. So ad hoc network basis, we know that whenever the device comes within the particular range, then the particular device will be identified automatically by the network. And when it goes out, again, that will be removed from the network. That's called ad hoc operations. Its low power computation consumptions limits transmission distance is up to 10 to 100 meters. Again, it is a line of sight communication. As it's a low power, the range is also very limited. Zigbee devices can transmit data over long distance by passing the data through a mesh network of intermediate devices. We can create a network of different Zigbee devices and try to communicate to quite far distances. But between any two devices, the communication can happen only in the range of 10 to 100 meters, not more than that. That too depending on the power of the transmission. If the power of the transmission is minimum, then it can be just 10 meters. If the transmission power is at a maximum available or the range, then it is 100 meters. It is typically used in low data rate applications that requires long battery life and secure networking. As I said, access control is used for the access control IDs are using Zigbee protocols. These operate at a bit rate of 250 kilobits per second. So there can be three types of or the three classes of Zigbee devices, that is Zigbee coordinator, Zigbee router and Zigbee end devices. Zigbee coordinator forms the root of a network tree and may bridge to other network. They actually form the network, and also these coordinators will be able to bridge between the different networks. Then the application whatever has to be run, that will be done by the Zigbee router, that will run the application. And Zigbee device, end device, uh, it cannot relay data from other devices. It is just it cannot be operated as the intermediate. It is a end device. If, for example, if we take a network of a devices, ZDD cannot be the intermediate device which will receive the data and transmit the data to the next module. No, that's not possible with the ZDD. ZDD is an end device. It cannot relay the data from other devices. It can only receive the data. That's the meaning of end device. So these were some protocols which we use in an embedded system. Thank you. If you have any questions, put it on the comments. Also, if you like the session, like the video. And if you have any specific topics to be covered, you can put it that also in the comment. Thank you.